Now, chapter 11, side problems. Now, page 200. Try this problem.
Okay, so we have a trapezoid, A, B, C, D. AD is equal to BC, so it's an isosceles trapezoid. We have a point E on DC, and we have a point H on AB, so that EH is perpendicular to AB, like that. And HB is 6, AD is 17, and EH is 8. So when I see this problem, I see that since AD is 17, BC is 17, and we can now ignore this left half of the trapezoid and just focus on this right trapezoid right here. Because if we draw a line parallel to BC, like that, so it's parallel, 17, this is 6, right? And let's call this point F. So we have 8, 17, and we have 15. So 15 and 6, we add those two up and we get EC is 21.
That's great. Can we also directly go from here? Can I also make
Yeah, you can make a parallel like that. Yeah.
How do we go from this time?
So if we make a parallel instead like that, then F would be over here. They're parallel, so this is also a right angle. This is 8. This is 6. So it's actually a rectangle. 8. This side length, FC, would be 15 now. And EC would then again be 21.
Okay, no, that's understandable. Makes sense. Now, chapter 11, side problem, page 201. Another trapezoid. Try this problem.
Okay. So we have DF is equal to FC. And from this notation over here, AB is equal to 2DC is equal to 4A. All it's really saying is that DC is split up into these two A's with DF and FC equal to each other. So we have A and A. It adds up to 2A. So DC is half of AB. So we have 2A and 2A down here because AE is equal to EB. And we have measure of angle V is 48 and measure of angle D is 138. So we have all three of these lines. So I would extend them up to this point. And because we go from 2A to A, and then we have A and A, this length here, ratio is K and K. Same thing here, which means they all intersect at a single point. Because they're at the same ratio, A to 2A, A to 2A. So they all intersect at the same point.
How do you use this angle?
Yeah, this angle right here, since in a trapezoid they're parallel, this is 42, this is 48, right? And this is going to be 90 degrees.
Top angle 90 degrees. That's very nice.
Yeah, which means that this K here is actually going to be A.
Because that length is going to be median, right?
Yeah, the median.
This is going to be the same length. And actually, whole things is median also, right? Here.
Yeah.
So
we have A. So this is going to be A as well. So EF is equal to A.
In terms of, okay, the value of EF is just A. yeah, we should not really think of this figure, right? And sometimes could be not drawn to scale, right?
Yeah.
Right. So we got this one. Now let's move to chapter 11, another side problem, page 202.
Okay, so we have a trapezoid. Um, and this one is a little bit weird. You have 4, 4, and this top side here is going to be 9. So like that. So it's 4, 4, 9. So we have measure of angle DAB is equal to 2 times measure of angle ABC. So what I'm thinking here is that we have parallel
Which two sides, sorry, Andrew, which two sides are parallel? Right. Can see.
AB and DC are parallel.
That's very nice.
So I see parallel lines, and I'm going to think, let's draw in this line AC, because by parallel lines, these two are equal, right? However, because ADC is isosceles, this is also equal, which means we've just made an angle bisector of DAB. And this is very convenient for us because now we split it up into 2 equal parts, and ABC is equal to exactly half of DAB. So this is also alpha, 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 alpha. And now we have an isosceles triangle. So these two are equal. And now what we have is we have similar triangles here because we have ACB, because that's an isosceles triangle with like these 2 angles of A. And ACD is also an isosceles triangle with 2 angles measuring A. So now we can set up this ratio. 9 over this length x is equal to x over 4.
So
Because of
Andrew, let's write the ratio 9 over
x
is equal to
x over 4
x over 4. Then
from 2
x squared
isosceles
equals
triangles. So x
36.
squared is 36, x is equal to 6.
Wow, very cool. Then where are we looking for?
BC, which is 6.
Yeah. Perfect, we got it. Chapter 11, another side problem from page 203.
Yeah, okay. So what I saw here almost immediately is we have this h squared is equal to a times c. So if I remember, this is a really important theorem in a right triangle. Whenever you have a right triangle and an altitude, we have h, and let's say a and c. H squared is equal to a times c.
Both
So
are perpendicular, right, Andrew?
yeah, they have to be perpendicular. That has to be a right triangle.
Mhm.
So I want to try to set this up, right? So what I try to do is we have this length right down here. This is C.
Mhm.
And now let's connect these two. And now all I need to show is that this angle is a right angle. And then we can say, since we already know this is a right angle, since it's a right trapezoid, we can say that h squared is equal to a times c. And what I notice here is that since this is C and this is C, right? That means they're equal. And since it's a trapezoid, these two sides are also parallel. And because there's a pair of sides like that that's congruent and parallel, we know it has to be a parallelogram. So these two also have to be parallel. And now we see from this line, if this line is a transversal on these two parallel lines, we have corresponding angles. We already know that that is a right angle, and that's where those intersecting diagonals being perpendicular comes into play, because now we know this angle is also right by corresponding angles. So now we can finally declare using this triangle, this theorem, that h squared is equal to a times c.
Great. So this theorem, under what condition, what two situation is correct, Andrew? The right trapezoid, it's got to be right trapezoid. What else?
Yeah. And the diagonals have to be perpendicular. That's very important because otherwise we wouldn't be able to declare the corresponding angles.
And then height square equal to the product of two
Bases.
bases, right? That's
Yes.
nice. And then the next problem, I'm going to relate that one to this one. Another side problem, page 205. Then how do we go from this problem, Andrew? Just our
So we just use the theorem. We have this right trapezoid, right? Uh, it's telling us it's a right trapezoid,
Mhm.
and the diagonals are perpendicular. Those are the two requirements. Common mistake. You need to make sure that the diagonals are perpendicular in order to use this. It's very important.
Then h is root 12, right?
Yes, using the theorem, we get h is root 12.
Then we are looking for DC actually, right?
Yeah. So
Then
DC, what
we
we would do,
can move to the height is here, Andrew. Then
yeah. And now we have this is root 12, 2. So that part would become 4. And now we have 16 plus 12 is 28. So this DC would be square root of 28, which is 2 root 7.
2 root 7. Because of we are using this triangle. Okay. We found that the height is root 12. This part is 4. And you take the square of both sides, and then you got 2 root 7. So that was a good application of that theorem. Now let's do this one. This is actually, it is just product of A and C, right? Okay. Okay, page 204 side problem. This is a proof one. Let's see. Where is A and where is B? So this is A, B is A, DC is C. Okay, then we are looking for this. Okay, Kn. First of all, this is equal. Then we are going to look for the value of x. What we remember from the similarity chapter, we did proof that time by using bow tie, and we are not going to go into detail this one. Let's say this is A, this is C, this is X. If we have these three parallel line segment, then 1 over X is going to be 1 over A plus 1 over C. Then 1 over X is going to be A plus C over AC. Then X is going to be AC over A plus C. Then we can see that the Kn, the value of Kn, is going to be 2x, which is 2ac over all over A plus C. So how do I see, Andrew, how do I see this figure into from this trapezoid?
Yes, well, we can see C is parallel to A. It says in the diagram Kn is parallel to AB, which is parallel to DC. So all three of the lines are parallel. And we have the same shape of the two triangles and the intersection point. So we can declare that it's X.
Mm-hmm.
And the way that we show that KO is equal to ON is we say we have these two triangles as well. So that means that using the theorem again on KO this time, we get that this is also X. So KO is equal to ON. Not only that, but KN is equal to 2 times A times C over A plus C.
Oh, thank you for completing that part as well. KO equals ON as well. That's great.
Yes.
So that was the end of the chapter 11 side problems.